Right. Thanks everyone for sticking around. Our next tutorial is from Mateusz Ruszkowski, non-thermal effects in the AGN feedback loop in the CGM. Thank you for joining us, Mateusz.
Thank you. Thank you for this opportunity to tell you a little bit about how non-thermal effects may operate in CGM of massive elliptical galaxies and clusters. And so in a nutshell, I'll talk about basically two things: how things are going up by feedback and how precipitation leads to accretion, and what role in these processes cosmic rays, magnetic fields, and turbulence play. So since this is a tutorial, let's start with something very basic. So here we have a cluster that is radiating, so it's losing energy, and therefore gas is accreting to the center, unless this accretion is then followed by this burping black hole that is producing these bubbles. And so a number of people looked into this problem. Here is an example of a simulation from Martizzi et al. And there's a long list of papers here, and hopefully you will find yours on this list. If not, then I apologize. The main unifying theme here is that all these simulations are hydrodynamical, so there are no cosmic rays and no magnetic fields. But if we look at these structures here and change our glasses and look at radio emission, then you will see that there are cosmic rays here. They are filled with radio emission and presumably, therefore, magnetic fields and cosmic rays. And so we see cosmic rays pretty much everywhere in space, going from small things, quote unquote, small things like the sun, all the way to pulsars, supernovae, starburst galaxies, AGN that we will be talking about, and even this sausage cluster present during collision. So this whole business started with Victor Hess, who discovered cosmic rays, as Peng mentioned yesterday, and Victor Hess got even a Nobel Prize for this work. And so cosmic rays play an important role, and so therefore it's important to ask some very basic questions about the physics of cosmic rays. And again, since this is a tutorial, some very basic physics for you. So to first order, we can treat cosmic rays as a fluid. So you have here some mousse here on ice moving, getting advected. Since this is fluid, approximately, we can also talk about pressure forces. And so those will be important. That can move gas around. And finally, we also have some other mechanism here that in addition to advection that you can see here, cosmic rays can also move around and disperse a little bit. So this is this diffusion and streaming that we've been talking about. And there is a little bit of subtlety involved in this last process, and I want to go over some topics that Peng also alluded to a moment ago, yesterday. And so this is a cosmic ray that is gyrating along magnetic field line. It's kind of moving like a bead on a wire because the gyre radius is very small. On the other hand, if gyre radius is very large, much larger than the fluctuations, then a cosmic ray just sees the mean magnetic field. So that's what we naturally expect. But an interesting thing happens at this resonance condition where these two length scale, a fluctuation length scale and gyre radius length scale, are comparable. And this is a complicated plot, but really the essence of it, the gist of it, is pretty simple. We have a magnetic field that looks like this fluctuating wave on a rubber band, and gyrating around it is this cosmic ray proton, for example. And at these three locations, you can calculate Lorentz force by looking at velocity, shown in this arrow, magnetic field, and the resulting force is acting to the left in this case. And there's always some net force acting on this cosmic ray proton. And the relative direction of this force depends on the phase of these two waves, but there is always some net force that doesn't really change the energy of this particle in the frame of this wave. And therefore, this wave can scatter these cosmic ray protons back and forth until their net drift speed adjusts to the speed of this fluctuating wave or Alfvén wave. And if you try to move these cosmic rays faster in one direction, they will have to lose momentum, lose energy, pass that energy to this wave. Wave will grow, and then subsequent damping of this wave will lead to gas heating. And so, not surprisingly, the heating of gas by cosmic rays depends on Alfvén speed and the pressure gradient in cosmic rays. These are necessary for this to happen. Also, we have this collisional heating where cosmic rays collide with ISM or ICM or CGM and produce other particles and gamma rays. So that's something to keep in mind as well. Okay, so we can now start constructing these basic models. We can start with some pressure gradient here as a function of radius, tangled fields, and a number of people worked on this over the years. And basic thing that I would like to start with is a simple estimate. We can take this heating rate due to cosmic rays and compare it to radiative cooling, and we can recast this in terms of something that is easily understandable. So plasma beta parameter, which is just the ratio of gas pressure to magnetic pressure, and that's a number that we know it's about 100 or 30. So this first number here is small. Cosmic ray pressure support is also small compared to gas, at least in large ellipticals. And these subsequent two numbers, ratio of height of atmosphere to cosmic ray pressure height, i.e. this thickness here, that can be a large number, and so is this precipitation rate, T cool to TFF. And so if you multiply all these numbers together, the thing that I want you to remember is that this number can be around unity. So in other words, in these diffuse halos, you can have heating comparable to cooling. Now, this works on a piece of paper, but devil is always in the details. So let's look at the devil here. This is what outflow from an AGN looks like. This is actually from the Virgo cluster. It looks more like this viscous fluid here. Doesn't really look like, let's say, flame from a cigarette. So there's some viscosity or submagnetic fields. As Johan just mentioned, viscosity is probably suppressed, so it's most likely magnetic fields. And you can actually trace their trajectory or shape by looking at H-alpha filaments superposed on X-ray emission. And you can clearly see that there is a laminar rather than turbulent flow. And there is a beautiful result that I recently saw that shows the radio emission from these objects. And it's clearly indicative of some presence of magnetic fields and cosmic rays. There's a simulation here that shows the draping effect and also the leaking of cosmic rays from those lobes. So magnetic fields play a role and cosmic rays play a role. And now we can start asking ourselves the question whether these simple estimates can be really realized in actual simulations. So there's a beautiful work from Christoph Frommer's group that looks at this, and it attempts to quantify heating rate from cosmic ray streaming instability that I just mentioned, and tries to compare it to analytic estimates that are guaranteed to have cooling versus heating balance that are shown here. This is from Jakob and Frommer. This is heating due to cosmic rays, this is conduction, and blue line is cooling. And so how do these analytic 1D models compare to these 3D models? Well, it turns out that these sophisticated 3D models actually oscillate around what is expected to have a successful heating model where cosmic rays play a very important role. Now, as I said a moment ago, not only do we have this streaming instability heating, we also have heating associated with collisions. And so this is to say that the amount of heating that you will get depends really on what these lobes are made of. And so this is an interesting result from Cross and others that shows that FR1s that are very common in cool cores can be proton dominated as opposed to FR2 sources that can be lepton dominated or electron positron dominated. So you can start wondering what sort of consequences this will have on the results. And so I want to draw your attention to this very beautiful result from Abdallah and others that looks at SZ effect. And these two blobs that are seen here indicate that basically these bubbles inflated by the AGN are devoid of hot medium. They have to be filled with cosmic rays, and folks simulated these kind of effects. This is from Karen Young and also from Christoph Frommer's group. And you can see these decrements or increments at the positions of these bubbles. And they can be only present when you fill these structures with cosmic rays, as opposed to the hot gas. If you fill them up with hot gas, then basically there will be no SZ signal. But with cosmic rays, there will be a missing gas, quote unquote missing gas. Now you can dissect it even more and look at basically what kind of cosmic rays do you have over there. If you fill these structures with protons, you will not exceed gamma ray limits, versus if you fill them with electrons, limits will be exceeded. And so that's another probe of what's going on and what these halos are actually populated with. Now, we don't really have time to go into this, but this is clearly related to the subject. So we have Fermi bubbles that also radiate because they are filled with some high energy particles that interact with CMB background. And there's a long-standing debate whether this is driven by stellar feedback or AGN feedback. And so I just want to advertise that this new result, the beautiful result from Erosita, that will probably shed new light on this and help us understand what actually is going on here. And specifically, Markus Bruggen and Kartik Sarkar will be talking about this next week. So I just can't wait to learn more about this. All right, so we talked about 1D models, 3D models. What if you let these jets pump more cosmic rays into these structures? So this is the closest cluster, MAT7, and you can see that as you go from the smallest scales where the black hole is to progressively larger, this basically shows you that the entire core is filled with cosmic rays. So what's their impact? So in order to understand what is going on here, you have to actually run these simulations for longer. And basically, in a nutshell, I want to argue here that physics really matters. So if you take just hydrodynamical simulations, their thermal content will quickly mix with the surroundings and it will probably work, but reality is more complicated. You have MHD and hadronic and Coulomb processes, and MHD will try to suppress this mixing, and these two other processes that are heating will not be particularly efficient in transferring energy from the bubbles to the surroundings. So we are back to what I was talking about in the beginning. You can have this streaming of particles out of these bubbles, and the streaming not only removes the particles from the bubbles, but it also generates this heating that I mentioned in the beginning that we estimated on this one of the first slides. So what do we get here? If you run this in two different settings, one with just hadronic heating and Coulomb heating, and the second case with streaming, you will notice that not only is the source more intermittent, but also the heating is spread and utilized very efficiently. And this has significant implications for whether you can actually support these atmospheres against catastrophic cooling. Now we can quantify this a little bit more. You can plot pressure support in cosmic rays versus gas. So this is what it shows you. This is pressure in cosmic rays divided by pressure in regular gas. Colors are dimmer when streaming is present versus colors are brighter when streaming is not included. So streaming basically reduces pressure support because energy of cosmic rays is utilized to heat the gas. And that agrees better with what's out there in the real world, in particular because streaming does not really produce gamma rays that could lead to some violation of Fermi constraints. So this model works reasonably well, and so we are moving to larger and larger scales. Cosmic rays have been also included in cosmological simulations with AGN. Only recently, this is an example from a fire simulation that shows energy density as a function of distance. And this is magnetic contribution. This is cosmic ray contribution here. And at the top, you have thermal contribution. So contributions are comparable here. And also heating rates are comparable. This is cooling rate, and this is cosmic ray heating rate. So there's progress and there's indication that cosmic rays can play a role in this context, cosmic rays specifically injected by the AGN. And so the claim has been made in this paper, also in Swiatsky and others, that cosmic rays and or combined with turbulence could suppress cooling flows in a cosmological session. Okay, let me switch gears a little bit. We talked about how things are getting out, and let's talk about how things are falling down and what role cosmic rays, magnetic fields, and turbulence can play here. So again, this has been going on for a while. This is an early simulation from Mike McCord that shows that you can have precipitation and accretion of these blobs when cooling is sufficiently fast. And again, a number of people contributed to this result, and a lot of progress has been made since then. So here are some examples from recent simulations that show the morphology of precipitating gas. These are quite interesting, and I believe we learned a lot from these results. So one thing that I would like to draw your attention to is that there is precipitation going on. This is the jet axis here in this direction, and there's lots of precipitation and lots of cold clouds. They are very clumpy, so that's one thing to keep in mind. Also, an interesting thing to notice here is that there are these disks, And this is seen in this simulation. Q and et al. Also show it. My own group also got the same result. Invariably, in these simulations, we get these disks, and they are very massive, and it's not exactly what we always tend to see in real world. In the real world, we have pretty messy distribution of clamps, as Johan showed. So these disks have to somehow disappear. And so I would argue that thermal instability has some important interaction with the magnetic field. And this is an example from the sun. You can see how thermal instability is strongly affected by magnetic fields. So we should add magnetic fields to these simulations. And again, here's a simulation that Sharon Wang performed. It shows pressure support due to thermal component and non-thermal component in the magnetic field in the bulk of the CGM in this giant elliptical. What is shown in red here is the enhanced magnetic pressure specifically at the location of the blobs. So basically, these cold filaments are magnetically dominated. This simulation also includes cosmic rays, but we didn't look at support due to cosmic rays. This has been done, for example, by Irina Butsky recently, and who demonstrated that cosmic rays can actually provide significant pressure support to these structures, which takes me to this question of whether you could power these blobs by cosmic rays and magnetic reconnection, for example. So what else can these magnetic fields do here? So if you take magnetic field and wrap it around this blob flying through the CGM and place it in a gravitational field, then magnetic tension will tend to extract angular momentum from this blob, and it will try to reduce its velocity, which is important from the observational point of view. There's also an interesting analogy to the morphology of this field and ramp pressure stripping, and I would like to point your attention to a Muller paper, Christoph Römer's also on this, that talks about ramp pressure interaction and magnetic fields. Now, so what do these magnetic fields do to these blobs as they are falling in this feedback loop? It turns out that you can extract this energy of these blobs very quickly by magnetic fields. This is energy of the blobs, and this is the rate of energy extraction. And the only thing that we have to remember here is that extraction timescale is about 10 million years in this particular case, which is interesting because if you look at histograms of velocities of these clouds, it turns out that instead of having virial expectation, which I'm just plotting with the cursor will be around here, you get narrower distribution if you add ramp pressure stripping that also Johan and I worked on, but you get even more suppression and even narrower distribution of this width of lines if you include magnetic fields. And I was really impressed with the first keynote talk by Xiaowen Chen, who actually reported on this kind of result in giant quiescent halos where velocities were actually smaller than expected. And so I would argue that this may be happening when magnetic fields are included. And this group here is not the only one that has done it. There's also interesting result by Freke van der Voort, who looked at the impact of magnetic fields with Arepo code. And so we find essentially the same result. Now I have 1 or 2 minutes. I want to mention one more thing. So we talked about cosmic rays, magnetic fields, and we just heard from Johan about turbulence. So turbulence, we like to describe using Kolmogorov spectrum and to describe this cascade. We can also describe it in terms of velocity structure function that is more easily observable, and Kolmogorov prediction can be translated into this velocity structure function that scales like separation between points to power of 1/3. And you can see more on this in Johan's tutorial and also Mark Voigt's and Sharon Wang's 4-minute videos. And so if we include magnetic fields in these calculations of precipitation and try to calculate what this velocity structure function will look like, it turns out that, first of all, morphology is very different in this case. Without magnetic fields, the distribution is very blobby. With magnetic fields, it's very filamentary. In both cases, actually, the velocity structure function or velocity separations as a function, velocity differences as a function of separation are non-Kolmogorov, which is a bizarre result. And I would argue that, at least as far as cold phase is concerned, one plausible explanation is that this has something to do with gravitational motion. So this plot, the second to last plot, shows mass that is flowing in and mass that is flowing out. So flowing out mass can be described using, for example, E1 Lee simulations. On the stuff that is falling down is described, for example, in Pratik Sharma simulations. We can look at specifically the infalling clouds that are falling down, and we can look, they dominate, and we can look at specific forces acting on these clouds. And it turns out that gravity dominates over magnetic forces. And if you just take two blobs and you let them fall down and look at how the velocity grows as a function of separation, you will get this scaling. And that's actually related to what Cameron just asked a moment ago, what will happen to infalling ramp pressure stripping galaxies. You would actually expect the same scaling. Last slide, what about hot phase? So hot phase can be stirred by the jet. This is velocity distribution and can be stirred especially efficiently when magnetic fields are present. So you can get more volume filling stirring. But we also have cold gas. There's lots of it. It is actually spatially correlated with the hot phase. And very importantly, the velocity variations are radially biased, which is what you would expect in the infall driven turbulence. Bottom line is that turbulence should be non-Kolmogorov. And I will just leave you with a summary slide. The main thing I was trying to convey here is that we have these three components, non-thermal components: cosmic rays, magnetic fields, and turbulence, and they are all interconnected and they all play a role. And whenever there is some puzzle, very often that puzzle can be addressed by invoking some of these elements. So thanks.
Thanks, Mateusz. That was a whirlwind. You covered a lot of material there. That was great. Are there any questions from the audience on these topics? It looks like Frank is first up.
Hi, Mateusz. Quick question. I mean, the interesting result that the Kolmogorov power spectrum slope changes, could this be related to the fact that when you have a magnetized medium and you start having all these vortice motions, you start actually having magnetic reconnection, magnetic processes that cause energy losses? And isn't this just an energy loss process that changes the slope?
That's an interesting question. Let me come back to this silly slide here because it has the right field morphology. So you have cold blobs, and the cold blobs, as they fall down, they bring magnetic fields with them, and the morphology of the field is as shown here. So the field goes this way, then turns around, and in the tail you have magnetic fields in close proximity, and they are anti-parallel. And so that's a prime example of where you would actually expect reconnection to take place. So that may be happening, although we didn't specifically look at this. There are some other papers. There's a paper I wrote with Eugene Churazov that looks at actually powering of H-alpha filaments using this mechanism. So this is happening, but as we know, to really model reconnection properly, you would need to resort to using some very dedicated experiments that are capable of resolving these structures extremely finely.
So it's not even, I'm not even talking about just the pure linear motion that you're reflecting here. It's also sort of the vortex motion that's inherent in the turbulence that will then cause a spin up of magnetic fields and reconnection.
Yeah, kind of, yeah. I mean, eventually this energy has to dissipate somewhere. That this winding up of the field will take place.
It's just that you have extra energy. You don't just transport all your energy to smaller scale. In the meantime, you lose some energy.
Yeah, I mean, at some small scales, you would start. This would start mothering. Yeah, I mean, that's probably interesting topic to look more into.
Okay, great. It looks like Frank froze as well, so I guess we'll cut him off there. Our next question is from Yang.
Yes, thank you. Mateusz, am I right with your name?
Mateusz.
Mateusz. Okay,
Yeah.
Excuse me. Yeah. In the beginning of your talk, you showed this work by Fabian 2003, where where the figure has H-alpha data overlay with X-ray. Yes, exactly. And then you said here it's more like a laminar flow instead of turbulence. Could you elaborate more on that? Like what is the physics behind it and why you think that's the case?
Yeah, so there is some indication, maybe this is a better picture to look at. There is some indication that these bubbles look more like bubbles in a jar of honey as opposed to, or bubbles in a glass of water as opposed to cigarette smoke. So these two situations are either viscous, such as in this case, or as effectively viscous, and that the viscosity, the stickiness, and non-ideal hydrodynamical effect can be caused by the presence of magnetic fields. So these will be effectively lower Reynolds number situations, and this is where the medium has relatively little stickiness to it and is more turbulent. So that's not what we really see. It's, how sticky it can get. Maybe it's even better shown here. You can see these strands. This doesn't look like a turbulent flow. It's quite likely that it is in the waves of these bubbles where magnetic fields are enhanced and they provide some pressure support. So this doesn't really behave like a real, like a simple fluid.
I see. So let me rephrase a little bit. So if you go back to the H alpha figure, what you are showing here is now we are seeing this finger-like elongated structure. So that's like the bubbles you're mentioning in the honey, and that indicates a high Reynolds number. That's why you have, okay.
Right. Yeah, so basically these structure here resemble what's happening in these vortices here. They are kind of, you could think of them as tracer particles. They are not going in random directions, right? They are following this pattern, which makes us think that either it's magnetic field or viscosity. But again, as Yuan mentioned, there are constraints on the viscosity. So it's probably magnetic fields that would also explain why these structures are shining in radio emission and heating the gas at the same time.
Sure. Thank you. Yeah.
All right, our next question from Rosie.
Hi, Mateusz. That was really interesting. Thank you for that. So you showed two simulations of AGN jets, one where you included cosmic ray streaming, and you could see that the heating was much more isotropic. So I was just wondering how you are injecting the cosmic rays in these. Yeah, that's the one. How are you actually injecting the cosmic rays in here, and kind of what fraction of the AGN energy are you assuming? And I just wondered what sort of constraints there are on how much you would expect.
Okay, yeah. So in these simulations, cosmic rays are injected through a jet that is anchored in the very beginning, in the very center of this domain. And we assumed that most of the energy in those jets is in the form of cosmic rays. So specifically 80% was injected as cosmic rays. So that's actually higher, substantially higher than in supernova case that Soching was talking about earlier. But there is a reason for the assumption that we made here, and I'm just going to go back to this slide, for example, that shows, that shows what happens when you fill bubbles with cosmic rays, right? So this is an actual observational result, and it's consistent with these structures being filled with cosmic rays entirely, and specifically with cosmic ray protons. So that's one example of how one can justify the assumption that went into these calculations. One thing to keep in mind here is that this situation differs from what you see in smaller halos. So in smaller halos, as Soching was arguing, you can have almost completely cosmic ray dominated CGM, versus in these more massive halos, pressure support due to cosmic rays is lower than, it's definitely subdominant. So it's kind of a different regime, but nevertheless, even though a relatively small amount of cosmic rays is present, they can actually produce a lot of heating. And maybe I didn't mention this clearly, but streaming heating actually dominates over hadronic losses. So I hope, did I answer your question? Or
yeah, okay. That's great. Thank you.
Yeah.
I have a perhaps naive question connecting Yong's earlier question about the Reynolds number and the relative role of viscosity with the tutorial that Yuan just gave, and that is, she was mostly dealing with larger structures like clusters, where she was seeing significant evidence for turbulence and turbulence playing a major role, whereas you were showing that in some of these cases, at least, the AGN cause, with the presence of magnetic fields, it's much more viscously, a lower Reynolds number. How do those two connect? Because presumably in these larger structures, the clusters, they do have AGN feedback going on in their central galaxy. So why do you see these discrepancies in the turbulent behavior?
One way to answer this is that in general, the effects of viscosity kick in on smaller scales, right? So, for example, a good way to look at this is to notice, to remind ourselves that plasma beta parameter is actually very high in these objects. So this means that gas pressure is much larger than magnetic pressure. And so gas pretty much moves the way it wants on large scales. But when you start looking at tiny things, such as, for example, these clumps that I mentioned at some point here, when I talked about what magnetic fields can do on small scales when you produce thermal instability and bring these magnetic fields together, then on those scales, actually this is maybe a better plot, on those small scales where these blobs are, plasma beta parameter is not 100, it can be a few, i.e. magnetic forces on small scales can be important. So on large scales, you could have turbulent motion, such as the one just talked about, but on small scales, it's like kind of, I always think about if you take a piece of paper and you start bending on large scales, that's easy, right? But if you take a pencil and try to bend it on small scales, you can't really do it. So turbulence on large scales and different and viscous effects on small scales.
Excellent. No, that was a great illustration. Thank you. The next hand raised from Daniel Wang.
Yes. Hi, Matthias. Nice talk. I do have a question. Actually, that's a follow-up of Yong's question. So you made an analogy with smoke from match, but I thought that there'd be different scales. Now you have like a Fermi bubble, whatever kind of simulation. You are on the scales of density scales or pressure scales. I thought that you see the top of the say X-ray, you see the top kind of more coherent features. I think that is more related to something like a nuclear bomb on ground. You see the mushroom coming up to the top. Then is kind of analogy, at least in my mind. So I thought that probably to do with kind of density and the pressure scale, like also like the sun, things happens there. Could you comment on that? And it seems to be your analogy on the match, smoke from match is much more small scales, kind of viscosity. Of course, turbulence plays a major role. But here it seems as kind of mushroom going up, into the atmosphere, then eventually flattens at the top because of the scaling of the, this happens all in atmosphere of the Earth, but also supposedly happens in the clusters of galaxies or even the CGM.
I will maybe you could point me to the right slide that brought that question.
But it's the same slide you used for the like honey whatever.
Okay.
Yeah.
Okay.
Go back, So that's fine. So this is like more like a mushroom of a nuclear bomb, and then the smoke from the from a match, you had on the right.
Oh yeah. Okay, and I'm sorry. Could you rephrase this question a little bit?
So my question is, this mushroom is much more on the scale which is comparable to the scale of density and the pressure of atmosphere.
Yeah. So you're asking about the physical difference between what we see here on the left-hand side and on the right-hand side.
Yes, exactly.
Okay. So the difference is caused by the following. So you have some gas here that has a certain entropy, and that entropy is larger than the entropy of the surrounding gas. And so in a nuclear explosion, or that you mentioned, or in this case here on the left-hand side, this structure will be going up until the point where entropy inside this bubble will be comparable to the ambient entropy. And apparently that's not the case here. So hence the difference.
Yes.
So this will start spreading like this laterally when this match of entropies is achieved.
Yes, that's basically either stability with basically the buoyancy.
Mm-hmm.
You know?
Yeah.
So that's actually the picture in my mind. But your analogy earlier made is kind of different. I mean, to the match, the smoke, the match. You know, so that I get a little confused.
Well, in both cases, it's buoyancy that's causing this. It's just that because the integrity of this bubble is not preserved due to lack of strong influence of magnetic fields or viscosity, that it falls apart and then mixes.
Okay, thank you, Mateusz. All right, we'll take one more question, and then I guess for consistency, we'll move to a breakout room for any follow-up discussions, even though I realize we don't have another presentation to occur. Christoph, would you like to ask your question?
Yes, excellent talk, Mateusz. So I would like to go back to the Sunyaev-Seldovich effect that you said may be able to constrain the composition. So, and I think it's difficult to do this at the low redshift universe because the equivalent magnetic field of the cosmic microwave background radiation that provides the sort of inverse Compton scattering is at 3 microgauss. In other words, if the true magnetic field is larger than 3 microgauss, electrons will mostly lose the energy via synchrotron emission that we can observe in radio. However, if you go to high redshift, say redshift 1 or so, then the equivalent magnetic field of the CMB is higher, and then provided the magnetic field within these bubbles is lower than the equivalent magnetic field, say whatever, 10 microgauss, then the electrons would mostly lose the energy via inverse Compton scattering, potentially be able to be observable. Is this what you were referring to, or did I miss something here with these gamma ray limits?
Honestly, the best way to look at this is to look at Karajan stimulation on this. They didn't look, as far as I know, they didn't include the effects of redshift on this. They're just isolated experiments as applied to non-cosmological. I think the best thing to do, the objective of this slide was to emphasize that these things have to be filled with cosmic rays as opposed to the hot gas, right? And we can have a debate on whether this is cosmic ray protons or electrons. And I think the very good venue for this would be the discussion close to the end of this workshop. As far as I remember, I think it's maybe 7th or 8th week where Daisuke Nagai and Nick Battaglia will be talking specifically about these issues.
Yeah, I don't think that actually they make a lot of gamma rays, especially at least at low redshifts, because electrons primarily cool via synchrotron emission, which in fact we already observe in radio. And you've seen this, you've shown this amazing Mercat observations where you can see individual magnetic flux tubes being lit up by the cosmic ray electrons there.
Yeah, so Karen Young obviously includes magnetic fields in her simulation, so they do have capability to include losses due to synchrotron emission as well. But we can look into this in detail and see, what are the caveats or not.
All right.
Okay. So thank you for the wonderful presentation, Mateusz. So we have reached the 10 o'clock time. For people who need to leave, obviously you need to leave. If there's further discussion, I mean, it's silly to go to a breakout room when everyone's here. So if people have additional questions, I saw Blakesley had her hand up a couple of moments ago. If there are any other additional questions, or Susumu had a comment in the chat that perhaps is worth discussing, I encourage people to raise their hands and we can continue with this for as long as we want, basically. But if people need to leave because we're at the end of our time, then people need to leave. So any questions from the audience or discussion points for Mateusz and his wonderful whirlwind coverage of AGN non-thermal processes?
I can ask my question really quickly.
Okay.
So yeah, I was curious, like in terms of like the change in slope of your velocity structure functions. So in the ISM community, there's been a lot of work on this, and basically the slope can be very resolution dependent. It could also depend on if you're more sensitive to like solenoidal versus compressive motion, in addition to, you know, all the other things that I've mentioned. So I don't know if have you done like a resolution study? Have you checked like a Helmholtz decomposition to see which modes you might have more of? I mean, those would be like the first things I think I would check if I was after, you know, exactly the scaling and what's causing it.
Yeah. Okay, good question. So in terms of the modes, I did not decompose this into solenoidal and compressible modes, but that's something that can easily be done. From previous work on this, if I remember correctly, there's a work that I did with Peng O on this, and if I remember correctly, the non-compressible modes were more abundant. But this is something that definitely can be looked at, and maybe this will actually shed light on what is actually responsible for this steepening. We had this debate, well, that maybe it's steering by AGN, maybe it's steering by the cold blobs, maybe gravity waves play a role, but looking at the compressible versus incompressible mode may be something that would provide further constraints. And as far as other question that you ask about resolution, yes, we did look at the resolution. And the solid part of this result is that resolution does not affect the velocity structure function of the cold phase, which is one of the main results of this paper. So the slope is steeper than Kolmogorov in the cold phase, and that conclusion did not change with the resolution. So that gives us hope.
Any other topics for discussion or questions from Mateusz? Oh, Max.
Yeah, thanks. I just want to follow up on the last question. I thought it was an excellent question. So do you have an idea what your numerical dissipation scale is here in this plot?
Yes, we looked into this by controlled experiments that actually didn't have any complications of the sort such as AGN or thermal instability. And we just basically took a stratified box such as, you know, this one, but without all these complications. And we steered it using actually non-solenoidal, solenoidal steering as far as I remember. In this simple experiment, we were able to look at where the power spectrum of the velocity structure function begins to bend over, at how small is that particular range. And for this simulation, for the simulation at this resolution here, that bending over began at about 0.8 kiloparsecs. So everything above that scale was safe.
Okay, can you go back to the plot where the 0.8 is? Sorry.
So that is about right here where these lines match, or right here where these lines match. Basically, when you see this bifurcation, is where the in the controlled experiment the spectrum started bending. But this range here, where the spectrum is clearly steeper than Kolmogorov prediction. The result was unaffected by resolution.
As a follow-up, do you in this experiment did you also include like the same refinement criterion you used for the rerun, and do you have any idea what the refinement does to this kind of turbulence, especially for the cold medium?
Yeah, that's a very good question. Unfortunately, there's no issue with this because we were kind of worried about this for a while. So what we did, we took this large box, which was about 0.5 megaparsec in size. What you're looking at here, by the way, this is just a zoom in on the very center, which is only a few kiloparsecs, about 10 or so. And we fully refined that region to maximum level of refinement, and we didn't touch that refinement at all. We just kept it. Basically, this is a uniformly refined box in the very center. And so, yeah, I was worried about the issue you just raised myself, so that's why we did it the way we did.
Thanks.
Brian O'Shea, do you want to? You've chimed in a bit in the chat relevant to the resolution and the codes that were used to resolve this. Do you want to ask those questions directly?
Oh, they weren't questions; they were statements.
Oh, okay. We have a Max, you have another question.
Wants to, I mean, it's to Mateusz, but also to the audience. I mean, I really like this, the last point exactly on this slide that you brought, between these connections of this trinity, right? And I mean, as you know, and we all know, we can't really resolve the small scale magnetic field structure and not the, not the small scale turbulence. So I was wondering how, what do you think is it, I mean, for instance, cosmic rays, how much can we trust, if we don't put this small scale turbulence and B fields in, and kind of a slightly different question related to the small scale turbulence. What's the state of small scale turbulence subgrid models employed in such simulations that you just showed?
Well, these simulations really don't have subgrid prescriptions for what's happening inside these cold clumps. The major subgrid prescription that is in this model that was present in the simulations that I showed in the end of this presentation is the prescription for energy injection by the AGN and the heating prescription for cosmic ray heating. But there are no prescriptions for what the velocity field inside the clouds is and how cosmic ray pressure affects the internal structure of these clouds. And that's not really something that is possible to even consider with these simulations at this point. I mean, you have to do what you, Max, are doing. You have to actually look at an individual cloud and then look at how magnetic fields and cosmic rays will affect, velocity, powering, and so on. We can just study global properties, bulk. Basically, the quote-unquote turbulence that we are talking about is bulk motions of gas on large scales.
Excellent. So perhaps a way of parameterizing the behavior in some of Max's simulations and feeding that back into the global larger scale.
Yeah. I didn't want to, self-advertise, or I wasn't referring to my kind of simulation. I was specifically referring to, subgrid turbulence models such as employed in, like global climate simulations, or I believe in supernova simulations, this kind of thing.
So we have a distribution of blobs. There's plenty of these blobs. They are flying through different environments. Some are in more magnetized environments. Some are in less magnetized environment. Some of the simulations include cosmic rays as well. So we have an ensemble of these clouds, and you could provide a prescription. I could provide a list of histories of these clumps and what fields they go through, what magnetic, what cosmic ray pressures they are encountering, and so on and so forth. And maybe that could be fed into your simulations to learn something about the statistics of these objects and what happens on small scales inside these clumps. Right? Because typically you take just one cloud and you put it in a wind tunnel, what if I tell you what the typical parameters that these clouds are experiencing in this ICM or CGM could be? And maybe you could learn something from that.
Question from Frank.
Yeah, related to this, the slope of the Kolmogorov spectrum, or the not Kolmogorov spectrum in the turbulence, given the problems on small scales with resolution, on large scales at least, you should measure it reliably. But the assumption is always that we're driving it at one scale, and then we should see a turbulent decay. But of course, the driving may itself have an entire power spectrum. So can you rule out that, for example, on large scales, you're just driving it with a power spectrum that is power half instead of 1/3, and you're fooling yourself thinking that you're seeing some deviation from turbulence? It's just the driving power.
Okay, so let me see if I understand the question. So you can obviously, large scales are resolved, right? Or you can clearly look how gas is stirred at large scales, whether it's by AGN or by infalling clumps. So on those large scales, you would also see departures from Kolmogorov. Right. I mean,
well, you see in the HD simulation, the hydro simulation, the MHD looked actually very nicely Kolmogorov, but the pure hydro one had a slope of a half.
They, when you look at cold phase, they all looked non-Kolmogorov.
Mm-hmm.
Yeah. So on large scales, they all look non-Kolmogorov, irrespectively of whether magnetic field was present or not. And the ultimate reason for this is that even with so this is a plot showing force versus time, and there are different contributions to forces acting on infalling clumps. The dominant force is gravity. It's essentially independent of time in this particular example. There is magnetic field that is also approximately independent of time, and there are other forces such as ramp pressure stripping forces as well. But the gravity is dominant, and so when you look at the clump that is falling from large distance, it's subject essentially to gravity. It's not exactly ballistic, right? It's not ballistic because there are these pressure forces from magnetic fields, but it's a constant force acting on this cloud. And if you subject infalling cloud to a constant force, it will give you this essentially this dependence. So that's why we believe that clouds that are cold are characterized by this sort of VSF. And the interesting thing is that these motions are radially biased. So that's something what you would expect in the precipitation model. They are not going sideways. They are not tangentially biased. So yeah.
Any other questions or discussion points? I saw a hand raised, but then it went down.
Well, I might as well just quickly say it then. So just in response to Max's question about the Trinity, one point is that we don't capture field line wandering in low resolution simulations. So that affects cosmic ray transport, and diffusion is effectively a sort of subgrid prescription for that. So it's just something good to keep in mind.
Okay, well, I encourage people. Oh, another question, another point from Max. All right.
Yeah, so what was then the difference regarding the power law slope? So what was the difference then between your simulations and the simulations from the last speaker, where she said she did see a Kolmogorov-like, so not this 1/2. But I mean, but if it's this gravity, I mean, I assume she also included gravity in her simulation. So what? Do you have an idea what could be this difference?
Physics in hydro simulations is the same, essentially. I mean, there may be differences in how the jet is modeled. And actually, Yuan is also on this call. I just scrolled down. I mean, in principle, there should be no difference. And by the way, just to be very clear about this, these simulations are intentionally presenting, or the way they've been processed is such that we intentionally stay away from projection effects. So what we are saying in these simulations is that intrinsically, these simulations, their turbulence, quote unquote turbulence, is non-Kolmogorov. So I actually don't know in Yuan's slide whether you were looking at projected VSF or not. Although you made an interesting argument that with projection you should get even steeper VSF. I mean, in principle, there should be no difference.
Projection makes it shallower.
Shallower. Oh, then
yeah. So if you see a super Kolmogorov slope in projection, which is what we did in the real observations, then the real slope should only be even steeper.
Right. And so what we are talking about here is this intrinsic three-dimensional turbulence. But even that should be Kolmogorov. Like, prior to us starting all this work and thinking on this, we expected that turbulence would be Kolmogorov, but even that wasn't. And so I know projection effects can mess things up.
Well, I thank everyone for their points, the wonderful tutorials from Yuan, Mateusz, and Suqing. I encourage people to use the Slack channels devoted to turbulence, devoted to cosmic rays, and devoted to magnetic fields for further discussion on this topic, because as we've noted, Slack stays around indefinitely, whereas the Zoom windows and chats don't necessarily. So please speak up in those venues and continue these discussions. And we will catch you guys tomorrow for Ellen Zweibel's keynote at 8 o'clock and follow it up with a discussion. So thanks, everyone. Wonderful job. We'll see you tomorrow.